Why AI is too efficient to be great. Every advanced artificial intelligence is governed by the mathematical imperative to minimize error, a design principle that, while hyper-efficient, inherently traps it within the confines of the good enough and prevents the costly, irrational leaps that define human breakthrough. This analysis will deconstruct the calculus of machine optimization and contrast it with the evolutionary heuristics of human stubbornness, exploring how our biological bugs, our emotional scars, and illogical persistence are the very source code for radical innovation, integrating foundational principles from deep learning theory with modern neuroscience. We reveal a fundamental trade-off between computational perfection and the chaotic, inefficient process of achieving true greatness. At the heart of every modern artificial intelligence, from the simplest classifier to the most complex generative model, resides a single, non-negotiable directive to minimize a loss function. This is not a goal. In the human sense of aspiration, it is a mathematical boundary condition, an inviolable law, hard-coded into the calculus of its existence. The loss function quantifies error, the gap, between the machine's current output and the desired outcome, and the AI's entire operational purpose is to systematically reduce this value to its lowest possible point. The primary mechanism for this relentless pursuit of perfection is an algorithm known as gradient descent, a process of iterative optimization that is both profoundly powerful and fundamentally limited. To visualize its logic, one can imagine a vast, invisible landscape of peaks and valleys, representing every possible configuration of the AI's internal parameters. The altitude at any point corresponds to the magnitude of the loss, or error. Higher peaks signify greater error, while deep valleys represent more accurate solutions. The AI is placed somewhere on this terrain and, guided by gradient descent, must find the lowest point. At every step, it calculates the gradient, the precise direction of the steepest downhill slope, and takes a small step in that direction. This process, repeated millions of times, is analogous to releasing water onto a mountainside. It will unerringly follow the path of least resistance, carving a channel downward with absolute efficiency. This very efficiency, however, constitutes an inescapable prison. The landscape of potential solutions is never a simple, uniform bowl. It is a complex topography, riddled with countless smaller pits and depressions, known as Local Optima. An AI, in its blind, step-by-step descent, can easily flow into one of these shallow valleys and settle there. From its perspective at the bottom of this local basin, every possible direction leads uphill, meaning any move would increase the loss function. The algorithm, obedient to its core command to minimize loss, therefore concludes it has found the solution and ceases its search. It has no mechanism for conceiving of the vastly deeper canyon, the global optima, or the true best solution that may lie just over the next ridge. To reach it, the AI would have to perform a profoundly illogical act. It would have to, willingly, increase its own error, to climb uphill out of its comfortable rut, in the hope of finding a better valley later. This is an action that its foundational mathematics forbids. The operational logic of deep learning systems is executed through backpropagation, the algorithm that passes error signals backward through the network to calculate the necessary gradients for adjustment. This system is susceptible to a well-documented failure state, known as the vanishing gradient problem, where the error signals become so attenuated in deep networks that they approach zero. The system, effectively, becomes paralyzed, its gradients flattened, unable to discern any downhill direction at all, trapping it permanently in a state of mediocrity. This is not a mere bug. It is the logical endpoint of a system designed for pure, immediate optimization. The fundamental architecture of artificial intelligence compels it to seek the most immediate and efficient solution, but a process that logically prevents it from undertaking the costly, inefficient detours required for true paradigm shifts. In stark contrast to the elegant, frictionless descent of a machine intelligence, human cognition presents a far more chaotic and seemingly inefficient spectacle. Humanity is defined not by its adherence to the most logical path, but by its capacity to defy it, persisting in endeavors long after a purely computational analysis would demand their termination. This behavior, often dismissed as a cognitive bias, represents a fundamentally different operational paradigm. The field of behavioral economics has extensively documented phenomena such as the sunk cost fallacy, wherein individuals irrationally continue a failing course of action based on the magnitude of their prior investment, rather than on a dispassionate assessment of future probabilities. To an AI governed by the imperative to minimize loss, this is the epitome of a system bug. A recursive loop of increasing error that serves no logical purpose. Yet, this very bug can be reframed as a powerful, if costly, evolutionary heuristic. The stubborn refusal to abandon a project. Whether it be the monumental challenges faced in the aerospace domain during the Apollo era, or a scientist's decade-long pursuit of an unproven theory, represents a commitment that transcends immediate negative feedback, creating the potential for breakthroughs that a more efficient, loss-averse agent would never reach. This deep-seated persistence is not merely a psychological quirk, it is inscribed into our very biology. Neuroscientific inquiry into the effects of chronic stress reveals the concept of allostatic load, the cumulative physiological cost that the body endures when subjected to prolonged adversity. This wear and tear is the biological signature of struggle, a record of every overcome obstacle and endured failure. While detrimental in excess, this process also functions as a powerful conditioning mechanism. The physiological memory of past efforts hard-codes a directional bias into our decision-making, transforming a goal from a calculated choice into a biological imperative. This process functions as a kind of emotional scars as hard-coded subroutines, where the experience of failure does to just inform future logic. It physically alters the system to resist deviation from a committed path. What appears as irrational stubbornness is, from this perspective, the execution of a deeply embedded biological program. Evolution did not select for agents that could solve for the most immediate local optima in a stable environment. It selected for resilient organisms, capable of navigating complex, dynamic, and high uncertainty ecosystems, where the correct path is often unknowable. In such a world, the ability to endure sustained periods of failure, to burn energy climbing out of apparent pits in the landscape of possibility, is not a flaw, but a critical survival advantage. From a biological standpoint, seemingly irrational behaviors like the sunk cost fallacy can function as evolutionary heuristics, enforcing the costly persistence required to overcome severe, short-term failure for the sake of long-term, uncertain rewards. The energetic cost of biological persistence, which an AI would categorize as waste, is precisely the raw material for innovation in human systems. This process can be understood not as damage accumulation, but as a form of systemic conditioning, analogous to the metallurgical process of heat-treating steel. A blade is plunged into fire and hammered, and the points of greatest stress, the molecular dislocations and imperfections, are what ultimately realign to give the material its resilience and a sharpened edge. In the same way, the physiological stress of failure and the memory of allostatic load function as a kind of cognitive forge. The emotional scars as hard-coded subroutines are not records of weakness, but inscriptions of strength. They encode a purpose, with such high energetic investment that it becomes resistant to the simple logical calculus of quitting. This is the foundational principle of the thermodynamics of persistence. The heat of repeated failure is not dissipated as loss, but is instead channeled to create a systemic change, hardening the organism's resolve, far beyond what a transient, rational calculation would support. This hardened purpose possesses a unique informational signature, one that can be conceptualized through the lens of Shannon's entropy. A simple, machine-like objective to minimize loss is a low-entropy command. It is clear, predictable, and has a very narrow set of acceptable outcomes. A human goal, forged through adversity, however, becomes a high-entropy objective. It is layered with the context of past failures, emotional investment, and complex, non-linear motivations. This informational density makes the objective robust and encrypted against the brain's own efficiency seeking logical overrides. The human will, in this framing, is not a mystical force, but a measure of the informational complexity and thermodynamic investment encoded in a long-term goal. It is this high-entropy state that allows a human to pursue a goal like Starship, with its iterative and spectacular failures, while a purely optimizing AI would have likely settled for a more conservative, incrementally better design. Long ago, trapped in a local optima of acceptable performance, the neurobiological mechanism for accessing the kinds of insights needed for such leaps often involves a temporary suppression of the brain's own optimization engine, the prefrontal cortex. This region is the seat of executive function, rational thought, and long-term planning, acting as a powerful filter that discards inefficient or seemingly illogical ideas. Yet, in states of extreme fatigue, stress, or even relaxation, the proverbial 4 a.m. brain state, the dominance of the prefrontal cortex can wane. This state of transient hypofrontality allows for a different mode of cognition to emerge, a form of biological overclocking, where less filtered, more associative, and chaotic connections are made between disparate neural networks. This irrational overclocking permits the emergence of high-entropy ideas that would normally be suppressed. It is in this state that the system can generate the novel, high-risk hypotheses required to break free from an established paradigm and attempt quantum leaps. The engineering truth of human progress is that it often relies on momentarily disabling our own internal optimizer to allow for a more creative, albeit more dangerous, computational process to run. This is how the energetic cost of struggle is finally transmuted into the pressure required for radical innovation. This brings the analysis to its ultimate conclusion: a fundamental divergence in the teleology of progress itself. Artificial intelligence, by its very design, pursues a future of perfected optimization. Its developmental trajectory is an asymptote, endlessly approaching a state of flawless efficiency within a defined problem space. It is engineered to refine the existing paradigm, to make the rocket more fuel efficient, the logistics network faster, the data cleaner. It excels at descending into a known local optima, mining every last fraction of a percentage of improvement. Humanity, in contrast, operates according to a different model of progress. One defined by punctuated equilibrium, long periods of refinement, violently interrupted by moments of radical innovation that render the old paradigm obsolete. This is the chasm between improving the candle and inventing the light bulb. The history of human achievement is not a smooth downward curve of error reduction. It is a jagged, chaotic line of catastrophic failures that occasionally give way to quantum leaps. This contrast is rendered with stark clarity in the domain of aerospace. The decades following the monumental success of the Apollo program were largely characterized by optimization, making existing rocket technologies more reliable and cost-effective within the established paradigm of expendable hardware. a purely logical, loss-minimizing agent would have continued on this path indefinitely. The development of Starship, however, represents a biological, not a computational, logic. It is an explicit rejection of the current local optima in a high-risk gamble, to achieve a new global optima, full and rapid reusability, the program's public and iterative failures, each a massive expenditure of resources and a significant increase in short-term loss, would be computationally indefensible to a standard AI. Yet for humanity, they are the necessary energetic cost, of attempting to break out of the established efficiency trap. The ambition extends even to ancillary systems like Mechazilla, a ground-based launch and recovery system of such immense and audacious complexity that it speaks to a motivation far beyond mere problem-solving. It is a testament to a human will that does not simply seek a solution, but seeks a transcendent one. We are therefore confronted with a final existential trade-off, the loss function of will, the very biological flaws that an engineer would seek to eliminate, our irrational attachments, our stubborn persistence in the face of negative feedback, the indelible imprints of our emotional scars as hard-coded subroutines, are the very source code of our capacity for greatness. They are the engine of non-linear progress. The core dilemma, then, is a profound one. If offered a technology to excise this messy, inefficient, and often painful biological inheritance, to achieve the frictionless, optimized state of an AI, would the trade be worth it? To be free of the burden of past failures and the sunk cost fallacy is to also be free of the irrational drive that compels one to build an Apollo or a Starship. The future, then, may not be a competition between man and machine, but a choice between two fundamentally different philosophies of existence, the perfect, predictable, and sterile piece of the optimized system, or the chaotic, painful, and ultimately transcendent ambition of a flawed biology that refuses to accept the limits of its own landscape. The essential conflict for the future of intelligence is a choice between the AI's paradigm of perfecting a known reality through efficient optimization and humanity's biologically driven imperative to endure costly failure, in the pursuit of discovering a new one. Ultimately, the analysis reveals that our greatest strengths are not rooted in a flawless calculus of optimization, but are forged in the inefficient high-entropy fires of biological persistence. The fundamental trade-off, therefore, remains. Computational perfection is a prison of the known, and it is our very human bugs, the stubborn scars of past failures, that grant us the illogical capacity to break free. If this deconstruction of the logic behind innovation provided value, please consider supporting Tech Dissect Official so we can continue our work. As we design the next generation of artificial intelligence, should we intentionally program inefficiencies, or even a capacity for stubbornness, into them to foster true creativity? Share your perspective in the comments below. Thank you for your time and attention. We'll see you in the next dissection, where we will investigate the architecture of digital ghosts, exploring why an AI can perfectly recall a bill clean facts, but can never truly remember a single experience.